Hello everyone, welcome to section 6.4. We have two things to do in this section. We want to use our knowledge of the inverse trig functions. We've spent a lot of time defining what they are, looking at their graphs, evaluating them. What we want to do is kind of start practically using the inverse trig functions. Really, they're one of, I would say, the most powerful tools we have in trig. Because what we can do is oftentimes when you're thinking about triangles, you don't necessarily know an angle, but you do know two sides. So what we're going to be able to do in this section is, given a triangle, if I know two sides of a triangle, I know everything about that triangle. I know the third side, and I know all three of the angles. Well, you'd already know one since it's a right triangle, but you would be able to find the other two. Then what we're going to do is we're going to do some exercises that have to do with composing trig functions and inverse trig functions together, visualizing them on with just a right triangle. A lot of these type of exercises pop up in calculus, so it's kind of good to visit them. Okay, let's get started. Okay, so let's see how we can solve a right triangle if we're only given two of the sides. So here's our first example. So let's say we're given this right triangle. Okay, this length here is 13, this is 12, and this is theta. And we're going to go ahead and we're going to try to solve this right triangle. Okay, so notice I don't know any of the angles. So what might be nice is we can actually, since I know these two sides, I can figure out what this angle is. If I know what this angle is, since I know that the sum of the angles of a triangle add to 180 degrees or pi radians, I could then use that to find the third angle. And I could also use the Pythagorean theorem to figure out the hypotenuse. Let's go ahead and think about how I could find the angle. So notice here, if we're thinking about SOHCAHTOA, then I can set up a trig function that has theta in it. Notice here that we know opposite and adjacent. So we know that tan of theta is equal to 12/13. Kind of move this over a little bit. 12/13. So what we would like to know is we would like to know what theta is. So what we can do here is we can apply the inverse tangent to both sides, or arctan. So we can apply tan inverse of both sides. So over here on the left, you can kind of think that I square rooted something and then I squared it. So these operations cancel each other out. It's like I multiplied by 3 and then divided by 3. These cancel out and I'm just left with theta. I did an operation to theta, I undid that operation to theta. I'm back at theta. So theta is going to be equal to the tan inverse of 12/13. So this is the exact value of this angle. Now 12/13 isn't a nice number on our unit circle, so what we're going to do here is we're going to use our calculators. Okay. So if you notice, right above the sine, sine, cosine, and tangent. So you know the sine, cosine, and tangent. This is harder than I thought. Right above them you see the sine inverse. Right above cosine you see cosine inverse. Right above tangent you see tan inverse. So we can use those buttons by first hitting the second button and then pushing where would it be, tan inverse to compute it. So we'll hit tan inverse and we'll just type in 12/13 and we'll hit enter. Now what it's going to spit out is going to, remember, inverse functions eat ratios and spit out angles. Now the angle it spits out is going to depend on the mode your calculator is in. Right now I'm in degree mode, so this is telling me that theta is equal to 42 point, how about we round to 2, let's round to 3 decimal places, 709, it'd be 7093, but I'll round to 3 decimal places, so 709 degrees. Okay, so that's how we find theta. Now if you had it in radian mode, let's see, we went to mode, and I was in radians, and I were to push tan inverse of 12/13, it spits me out 0.745. So what it spits out depends on what mode you're in. So degree mode. and this is radian mode. Radian mode. Okay, I'm going to go ahead and work with degrees from this problem. Okay, so now that I know this angle, I can easily find everything else I need to know about this triangle. Let's call this angle here, we'll call it phi. Now, since the sum of the angles of a triangle add to 180 degrees, and 90 of that is taken up in the right angle, these two angles must add to 90. So I know that phi must be equal to 90 degrees minus, phi. We know that phi, the other angle, is 90 degrees minus the tan inverse of 12/13. Notice I was just being a little bit careful. I know I rounded this answer, so maybe when I plug into my calculator, if I want to try to be as exact as possible, maybe you'll do 90 degrees minus the tan inverse of 12/13 to get the exact answer. 90 minus the tan inverse of 12/13. Try to be as accurate as possible. So this will be 89.25. If I'm rounding to 3 decimal places, I would put 5.5. This would be degrees. Okay. Now the only thing we don't know is the hypotenuse. How about we call the hypotenuse c? So we know that c will be equal to the square root of 12 squared plus 13 squared. So we'll have the second square root of 12 squared plus 13 squared. So maybe we'll do it exact. What's just 12? What's just 12 squared plus 13 squared? Okay, that's 313. So the square root of 313. So that's what c is. So now we know everything about this triangle. We know all of its angles, and we know all of its sides. Okay. Notice here, for example, just for fun, that we figured out that this length was the square root of 313. We could have used a different inverse trig function if we wanted to. This is just maybe something kind of just fun to do. Since I know all the sides, well, I don't necessarily have to use tangent anymore. Let's say we use sine, for example. So sine of theta, well, sine is opposite over hypotenuse, so that would be 12 over root 313. And then you could apply the inverse sine or arc sine to both sides. So here we get that theta would be the sine inverse of 12 all over the square root of 313. Now our calculator should give us the same answer. So let's go ahead and push the sine inverse of 12 divided by the square root of 313. So I'm in radian mode. Let's go back into degree mode. So I'm getting the same thing. I'm getting 42.709 degrees. How cool. Try it with cosine and cosine inverse. Make sure to pick the right ratio. How cool is this? All right. So let's have you try one. Okay. Let's say we're given this right triangle here. Let's say we know that this is 55 and this is 27. Go ahead and solve this right triangle. Okay, let's go ahead and do it. So we could easily find this side here. But I don't know, how about we find an angle first? Why not? Why don't we find an angle first? Let's find this one. It really wouldn't have mattered which one you wanted to find first. So let's see here. We know adjacent and hypotenuse, so we know that the cosine of theta is equal to 27 over 55. So what this means is if I apply a cosine inverse or arc cosine to both sides, that theta would be equal to the cosine inverse of 27 over 55. Now maybe for fun, I'll just write arc cosine here for you. They mean the same thing, Maybe just to kind of get you thinking about that notation if you see it in other classes. Okay. I oftentimes in my calculus classes will usually try to use the arc cosine and arc sine because I don't know, I feel like there's less confusion for students thinking that this means 1 over cosine, which it does not. 1 over cosine is what we call secant. This means cosine inverse. So we'll use this version more in this class because that's the button you have on your calculator. Okay, so let's go cosine inverse of 27 divided by 55. Okay, so I'm getting that theta is equal to, looks like 60 point, let's see, this would be 5996. I'm going out to 4. So what would I do? I'd round this number up, which would round this number up. So I would write 60, round this number up, 60.6. I guess you could put 0, 0 if you'd like. Okay. Degrees, I'll erase those zeros. Okay. Let's go ahead and let's find the other angle. Find phi. So phi is going to be 90 degrees minus the cosine inverse of 27 over 55. Okay, let's see what we get. So 90 minus the cosine inverse of 27 divided by 55. And I'm getting 29.40035. If I'm rounding to 3 decimal places, I'll just put 4. I guess you could put 00, but I'll just write it. 0.4 degrees. Okay. So that's what I have for phi. Okay, what else don't we know? We don't know this side over here. I don't know, how about I label that with an H? It looks like a height to me. Okay, so, I mean, for fun, I'll show you 2 different ways to find H. I mean, the easiest way is to just use the Pythagorean theorem. We'd have that the square of the hypotenuse is equal to the sum of the square of the legs. So we'd have that H would be equal to the square root of 55 squared minus 25 squared. Okay, what's 55 squared minus 27 squared? We get the square root of, this is the square root of 2296. I doubt this is a nice number. You can just do to the power of 0.5, 1/2 power, 47.9165. It's not a nice number. I'll just leave it like this to have an exact answer. But maybe we can get a feel for what it is. This is, they're saying that this length here would be 47, roughly 47.917. But for fun, since we know what these angles are here, well, we could say that what was this, roughly 60.6 degrees? So we could say that how about the cosine, or let's do the tangent. So we know that the tangent of this angle, which was roughly 60.6 degrees, well, that's equal to h over 27. So h is going to be 27 times the tangent of 60.6. So let's see what we get here. 27 times the tangent of 60.6. And I'm getting, no way, 47.9917. The same thing. So it's nice that you can see all these tools really do work and work well together. And I don't know, this is what I oftentimes think about. What's so fun about math is you have all these tools at your disposal. As long as you're approaching it right and setting things up right, you can approach problems in so many different ways, and I don't know, it's just fun. Okay, so we've solved this right triangle. We found all these angles. And we found the extra 2 angles, and we found the last side. Here's its exact answer. And I guess if you wanted the exact answers of the angles, theta is exactly equal to the cosine inverse of 27 over 55, and phi is exactly equal to 90 degrees minus the cosine inverse of 27 over 55, if you'd like. Okay, what we'd like to do now is take a look at some composition exercises. Okay. So some composition exercises. Okay, so what's nice is when you compose a inverse trig function and a regular trig function, you can often evaluate those without having to use your calculator, and you can do it just by thinking about what they mean and thinking about specifically what they mean on a right triangle. So, for example, and I do have to say that these types of exercises do pop up in calculus, so it's good to see them now. Let's say that we want to evaluate the sine of the cosine inverse of 12/13. Now we're going to do this without using your calculator. I mean, you could easily just plug this into your calculator, but where's the fun in that? Where's the fun in that? Okay, so let's figure out what this means. What does this mean? So whenever you're doing a composition, what you want to do is you want to work from the inside out. So let's think about what is cosine inverse? What is cosine inverse of 12/13? We have to remember, what does cosine inverse spit out? Remember, inverse trig functions, they eat ratios, and they spit out angles. They spit out angles. They spit out angles. So what this thing is inside of sine, this is an angle. This is an angle. I'm taking the sine of this angle. Okay. So now I just need to know a little bit of knowledge. Is that red kind of really hard to see? Let's use something a little bit better. Here, a blue. Theta is the cosine inverse of 12/13. Inverse functions spit out angles, and we're trying to take the sine of this angle. Now, this right here is pretty much telling me, maybe you don't see it right away, this is telling me that I know two sides of a right triangle. What is it saying? Well, if theta is equal to cosine inverse of 12/13, you could apply cosine to both sides. This implies that the cosine of that angle is 12/13. The cosine of that angle is 12/13. These are equivalent statements. So this is whispering us secrets of this right triangle. It's whispering. It's saying, hey, cosine is adjacent over hypotenuse. Hey, adjacent, hypotenuse. We know information about this triangle. It's whispering. Adjacent is 12. Hypotenuse is 13. Thank you. So now, what are we really trying to compute? Well, from the beginning, we're trying to compute sine of this cosine inverse thing. Cosine inverse is our angles. What do I want? I want to know sine of that angle. What is sine of this angle? Well, sine is opposite over hypotenuse. So I gotta figure out what this height is. I gotta figure out what opposite is. Let's call it, I don't know how we call it, h. No, don't get confused with hypotenuse. I'm thinking height when I'm writing that. So what would h be? Well, h would be the square root. You would take the hypotenuse squared and you would subtract this leg squared. So what is h? What is h? Let's see, what is 13 squared minus 12 squared? 25. This is the square root of 25. So this is just 5. So I know that this height, or this opposite side is 5. So now I want to know, this is saying, what is sine of that angle? Well, sine of that angle is what? Opposite over hypotenuse. It's 5/13. How fun! Look, we did this without a calculator. We just drew a picture and thought about what all the pieces mean. So sine of cosine inverse of 12/13 is 5/13. Okay. Let's have you try one. Okay, let's say we have the cosine of the tan inverse of 7/24. I want you to pause the video and try to evaluate this without using your calculator. This is 7/24. 7/24. Go ahead and give this a shot. Okay, let's do it. So the first thing I'm going to realize here is, what does a inverse trig function spit out? Angles. This is an angle. And what we're trying to figure out is, what is the cosine? What is the cosine of that angle? Okay. Well, the angle is what tan inverse is spitting out when you plug in the ratio 7/24. But this is whispering to us. This is whispering us some information. It's saying, hey, if theta is the tan inverse of 7/24, then, well, that means then the tangent of theta is equal to 7/24. And this is saying, hey, remember tangent? Remember tangent is opposite over adjacent? This is saying, hey, the opposite is 7, the adjacent is 24. Sweet! Let's draw it. Here's theta. Opposite is 7, and the adjacent is 24. So here we have it. This is the triangle, but what do I want to know? I want to know what cosine. I should color this blue. I want to know what the cosine of this angle is. Well, how can I figure out what the cosine is? Well, I would just need to know what adjacent over hypotenuse. I got to figure out what the hypotenuse is here. Let's call it c. So we would have that c would be equal to the square root of 24 squared plus 7 squared. Let's see what this is. 24 squared plus 7 squared. This is the square root of 625, which I believe is 25. Yeah, sweet. 25. Who came up with these nice numbers? Okay, so we know C here. We know C here is 25. So what we're trying to figure out is, what is cosine of this angle? What is cosine of that angle? Well, cosine is opposite over, cosine is adjacent over hypotenuse. 24 over 25. Fun. Fun. Okay, and there we have it. Okay, hopefully that glare is not too bad. I apologize for the glare. Okay, let's do this a little bit more generally. Oftentimes, the types of exercises you'll see that have to do with this in calculus oftentimes don't have numbers. So let's do this a little bit more generally. Okay, so as an example, let's say that we know sine, or we're trying to evaluate sine of the tan inverse of x. What I want to do is I want to express this without any trig functions at all. Express. I need a better marker. Express. Without trig functions. Go ahead and think about this for a second. Pause the video and see if you can think about, how could I write this with kind of knowledge of what we did in the past exercises. Could you somehow think about a way to draw a right triangle and express this without any trig functions? Give it a shot. Okay, so just like how we did the last exercises, what we know that inverse trig functions do is they spit out angles. So we want to know what is sine. We want to know what is sine of this angle. Well, what is this angle? This angle is the same thing as the tan inverse of x. If we applied tangent to both sides, this would be saying that x is equivalent to the tangent of theta. But this is whispering to us secrets about this right triangle, because this is a ratio. This is x over 1. So this is telling us that since tangent is opposite over adjacent, opposite is x and adjacent is 1. This is telling us, this is whispering to us, that the opposite is x, and the adjacent is 1. And this is theta. Now what do we want to know? We want to know sine of this angle. Sine is opposite over hypotenuse, so we need to know what the hypotenuse is. We'll call it c. So what we have here is c is going to be equal to, well, it'd be c squared would be equal to x squared plus 1 squared, or I hope you believe you'd see this with c, would be equal to the square root of x squared plus 1. And that's what we have here. This is the square root of x squared plus 1. So what is the answer? We want to know what sine, what sine of this angle is. Well, what sine of this angle? It's opposite over hypotenuse. It's x all over the square root of x squared plus 1. So that's what we have here. Isn't that kind of cool? This is saying, just write it so there's not so much here. This is saying that the sine of the tan inverse of x, this ugly trig expression, can be written just as x all over the square root of x squared plus 1. Cool. Cool. This is so much nicer. This is so much nicer. So much nicer to work with. Okay. Let's have you try one more, just for good practice. Okay, let's say we have the tangent of the cosine inverse of x. I want you to pause the video and try to express this composition without any trig functions at all. Give it a shot. All right, let's do it. Let's do it. So cosine inverse spits out an angle. We're trying to figure out what tangent of this angle is. What's tangent of this angle? Okay. Well, what is that angle? That angle is cosine inverse of x, which means that the cosine of theta is equal to x. Think of this as x over 1. This is whispering to us information about a right triangle. Okay. Cosine is adjacent over hypotenuse. So we need to figure out what this height is right here. So we would have that 1 squared is equal to h squared plus x squared. Okay, if we're solving for h would be equal to 1 minus x squared, since this is 1 squared is just 1, and I'd be square rooting that. So h is equal to the square root of 1 minus x squared. And what do we want to figure out? We're trying to figure out, I have it written right here, but we're trying to figure out what is tangent of that angle. Well, tangent of that angle, tangent is opposite over adjacent. So that's going to be the square root of 1 minus x squared all over x. Yeah, this is the same thing. This is the same thing as the tangent of the cosine inverse of x. How fun is this? That's so cool. Awesome. All right, so that's all I have in this video here. What we're going to be doing in the next couple of videos is here we've been solving right triangles. Given a right triangle, given information about it, we can find all the sides and all the angles. But what if we don't have a right triangle? How do we solve a general triangle? We'll see you there. Take care.